class. Today we are going to learn about the calculation of density. That means how to find the density of the solid. Okay, so obviously that will be related with the mass and volume. So now we will know how to calculate this, the volume, that density of a unit cell. Okay, so let's move to, this is the heading, that is calculate the density of cubic crystal from its edge. If we know the edge length or the radius of the unit cell, then how we will be able to find the density with this. So let's suppose that unit of edge of the unit cell is a picometer. Some a is the side length, okay, and if the number of per unit cell, I'm just considering it as a z, okay. This is the as I told you in the starting also, I have told you the rank about this Z. That means it will tell you the number of atoms per unit cell. For BCC it is 2, for FCC it is 4, for primitive it is 1. Yes, so that is like atomic mass of the element is M, capital M, and mass of each atom I am considering small m. So if I want the volume for this, so what I have to do? Volume is equal to A cube, because you that length cube ho jayega, and this is in the picometer, so I'm going to convert it into centimeter cube. So that's why picometer is converted into centimeter by multiplying 10 to the power 10. So it is cube, so that's why it will be 30. I hope it is clear. Okay, so density of the unit cell is equal to whatever the density we know. Density will be equal to mass upon volume. Density of unit cell will be equal to mass of unit cell upon volume of unit cell. Mass of unit cell, how it is not mentioned, but mass of each atom is mentioned. Yes, so can you find the mass of unit cell? In one unit cell there will be some number of atoms. Yes, and each atom mass is m. So can I say the mass of unit cell will be z into m or m into z? Yes, total number of atoms present in that and mass of each atom, multiply kar do, you will get the mass of unit cell, isn't it? So this is the z into m. Now volume of unit cell, right now we calculated a cube into 10 to the power minus 3 minus 30 centimeter cube. So mass of each atom, how you will find this? Like, say this is mass of each atom is equal to m, and this m can be equal to this. How come? In that mole concept you have done that number of atom is equal to this formula. You have done number of atoms is equal to weight by molecular weight. Let me write. So this was the formula. Number of atoms is equal to weight upon atomic mass into Avogadro number. Yes. So now number of atoms is equal to, suppose that 1. If I have to find, so what it will be, this weight of one atom will be equal to, can I write this weight will be equal to number of atoms multiplied by atomic mass upon Na? Yes. So that is the mass of each atom. We can calculate by this way. Any problem in this? Got it? So this is the number of atom multiplied by atomic mass into Avogadro number, and number of atom I am like it is one atom each atom, so that's why I'm considering 1. Upon atomic weight I have given the abbreviation capital M and Na, we know that. So can I write this mass of each atom value? This is this equal to that Z into M ki jagah pe, can I put this value? Yes. So that is the formula. So now mass of unit cell we got it, and now this is the formula, density is equal to, so here you got the mass of unit cell, what, Z into M upon Na, and volume of unit cell A cube. So just put this, you will get this. Got it? So this is Z into M, Na into A cube. This A must be in the picometer. If you are doing in the centimeter cube, what you have to do? It will be 10 to the power 30 over here. If you will write a So this will be 10 to the power 30 will come up like as a numerator in gram per centimeter cube. The unit will be here gram per centimeter cube. But if you keep gram per picometer, this is gram per picometer cube. This is the formula. Got it? समझ में आ गई बात? Any doubt in this? So this is the formula for gram per centimeter cube, and if it is in picometer, you can directly write AQ. So that is the formula for finding density. Now question can be asked like here 3-4 variables are there. Density is one. Now rank is another thing. Atomic mass, Avogadro number, and edge length. 5 variables are there. Although we know that Avogadro number is a constant, but sometimes it is asked that what will be the Avogadro constant value. So in that type of question, the calculation will be most easiest one. Yes, what to do? We have to put the value of all this thing. Density kya hai, Z kitna hai, M kitna hai, AQ kitna, so all the value we will put, and around approximate jo Avogadro number hota, that we will write. Will not write exactly 6.022 into 10 to the 23. We will just little manipulation will be there, and we can write 6.019. But yes, order should not be changed. 10 to the power 23, so that should not be changed. 6.019, you can say 6.024 to 6, like you can say, okay, approximation value. But this 10 to the power 23 should not be changed, and 6 also, that should not be changed. Got it? So it can be asked like this is the density, this is the edge length, mass, so atomic mass is given this. So what will be the rank of that unit cell? Rank means Z. So you can find in this way. Anyway, the question can be framed. Okay. So let's do some questions. The first question is here. An element, atomic mass 50 gram per mole, having FCC structure, has unit cell edge length 400 picometer. Any A is given. Yes, atomic mass is given. FCC यानी कि Z is given. Density आपको निकालना है. So simple formula, isn't it? Weight upon atomic mass. Here you can say that weight upon atomic mass into the density is equal to A upon AQ, like Z into M upon AQ into N. That formula you have to apply and you will get this. Yes. So let's do this. Here mass is equal to 50 gram. Yes. Atomic mass is given. Z is equal to 4 FCC की वजह से A is 400 picometer. Convert it into centimeter. So this will be 4 into 10 to the power minus 8 centimeter. If nothing is given, you can write in gram per picometer cube also. Got it? So in that also, that unit also you can find, but most probably and most acceptable one is centimeter. So you are supposed to write you are supposed to convert this unit into the gram per centimeter cube. Got it? Okay, so this is density is equal to Zm upon Na into AQ. Formula is there. Z is equal to 4, atomic mass 50, Na this. This is Na here I have written, and this AQ is volume. Calculate it, you will get this value. This is the density. Got it? Here's another question. In this question, we are supposed to find that number of atoms in 100 gram of a BCC crystal lattice with the density 10 gram. Here, that in 100 gram you have to find, okay, BCC is given, so that means Z is equal to given, density is given 10 gram per centimeter cube, edge length is given. So by this way, you just find the molecular mass first. Molecular mass you will get by the same formula. Yes, density is equal to Zm upon AQ into Na. So use this formula, you will get that. Here it is in picometer, but density is given in centimeters cube. So I'm supposed to convert this into centimeter cube, and that's is necessary. Okay, if it will not convert, it will give you the different answer. Okay, so by putting the value of all this value, I have put that density is equal to 10, and this A cube is given 10 to the power 8, so it will be, sorry, it should be minus 8, no? should be -8. It's not working. What happened? This is minus. Okay. So in this way, you will solve it. You will get like this. Any doubt in this? Okay. So now, you know the formula that number of atoms is equal to weight upon molecular weight into Avogadro number. Again, the same thing. Let me do it. Let me write this. Okay. So this is the formula: number of atoms is equal to weight upon atomic weight into Avogadro number. What you are supposed to do in 100 gram. So just put this 100 gram. You can find the number of atom over here. 100 upon atomic weight, you got this 3.016 into Avogadro number. You just put it, you will get this answer. Here I have done in another way. First I have this is the formula I have used and I got this one atom. It's not required. You can use this directly formula. No? This one is not required. You can use in this way directly. Okay. This is weight is equal to 100. Avogadro number this much and atomic weight we got this. Just solve it, you will get this 2 into 10 to the power 25. This is the another way we can solve it. Like first we will find that the 1 gram mein kitne honge. In the same way, one atom I am considering, so this will be 3.Na here upon 3.016, isn't it? Number of one atom agar hum nikalte hain 1 gram ke liye, so and for 100 gram 100 se multiply kar denge, so this is the same way. Or you can do directly this formula, use this direct formula and solve it. Got it? Okay. Now another topic, and this is towards the end of the chapter. Okay, that means imperfection in solid. Solids we put it, we all that keep the things, keep the solid together, but still some imperfection is there. Imperfection ka matlab kya hota hai? It can be of different type. So imperfection, that means something with which is other than the expectation, other than the pattern. Okay, if there is no pattern followed, whatever the expected one, so then it is called imperfection. Yes. So let's do this. Any departure from perfectly ordered arrangement of a constituent particles in crystal is called imperfection or defect. Clear? Types of crystal defect, it is of two type: point defect and the line defect. Point defect, as the name suggests, एक point पे problem होगी. Yes. The irregularities or the deviation from the ideal arrangement around a point or an atom is known as point defect. As for example, like we have solved so many numericals in that particles are arranged at the corner, at the edge center, at the BCC, something like that. And if I'm saying that if the corner particles are removed, if one BCC particle is removed, if one FCC particle is removed, then what will be the formula? So that is one I'm mentioning that point. So that is called point defect. But whatever the question we have done, that through an axis the atoms are missing. So that is a line defect. I hope it is clear. So if the defect is in the entire row of the lattice point, then it is known as line defect. Clear? Now, types of point defect, if we go, it is of three types: stoichiometric defect, non-stoichiometric defect, and impurity defect. One is that stoichiometric, non-stoichiometric, and impurities. So if we check this, this is stoichiometric defect that can be called, there are the two names for this. One is called vacancy defect, another is called interstitial defect. Okay. It is a kind of point defect in that the ratio of positive and the negative ions, which is stoichiometry, which gives the stoichiometry, and the electrical neutrality of a solid is disturbed. जो disturb हो जाता है. Like earlier, if it was like equal number of cations and anions are there, and one cation or one anion is missing over there. So it is going to disturb the electrical neutrality, isn't it? And the stoichiometric coefficient also, suppose the 7 or what is this? Like I have another GIF also, I will show you. Okay, so that means here it is at 1 point se gayab ho raha, one lattice se gayab ho raha, so that's why it is called point defect, and that is creating a vacancy over there, over that site. So that's why it is called also called vacancy defect. Clear? Sometimes it is also known as an intrinsic or thermodynamic defect. Thermodynamic defect ka matlab, if this defect arises due to the temperature. If we increase the temperature or we heat this crystal, so what happens? The one unit cell, that one lattice point get disturbed. it creates the vacancy over here. So that's why it is also called thermodynamic defect. Fundamentally, they are of two types. First is vacancy defect, which I have explained, where an atom is not present at their lattice site. अपने lattice site पे present नहीं है, and the site is vacant, due to which it is creating a vacancy over here, and that's why what? Electrical neutrality is also disturbed. Okay, and now what will happen? This was the volume and this was the number of atoms, suppose at mass per unit volume. Now one atom is missing over here. So mass will be decreased, isn't it? So what will happen? The density of the substance will also be decreased. Clear? Koi dikkat, any problem here? Because one mass is like one point is missing over here. So mass is less, volume becomes increased more, and volume increase, so density will be less, isn't it? So that the density is decreasing. Another is interstitial impurity. Interstitial impurity, what will happen? That the particle from its lattice site निकल के what happened? Another unit cell के interstitial में जाके बैठ गया. You know, so it is like two molecules are there. If I'm heating one unit cell के वहाँ से vacancy create करके, it goes to the another crystal, another unit cell. Okay. So, interstitial defect, it is a defect in which an atom or a molecule occupies the intermolecular space in a crystal. In this crystal, what will happen? Number of atoms increases, so mass increases, and mass increases, volume decreases. So, what will happen? Density will also increase. So, ये याद रखेंगे, interstitial में आ जाता है, and due to which it increases the density. Hope it is clear. These two occurs in a non-ionic compound, like vacancy and interstitial impurities. They occur in the non-ionic compound. Okay, a non-ionic compound mainly shows vacancy and interstitial defect. An ionic compound shows the same, but in another name, and that is called Frankel and Schottky defect. Clear? The interstitial defect, interstitial impurity, and the vacancy defect is shown by non-ionic compound. While the ionic compound, they show the same thing, but the name will be different, and the name will be Frankel and Schottky defect. Let me explain that. So Frankel defect, what it is? Frankel defect in ionic solid it occurs. Okay, generally the smaller ion, the cation जो होता है, that moves out of its place, अपनी जगह से हट जाता है, and occupies an intermolecular space. Anion cannot occupy the intermolecular space because anion size is bigger, isn't it? So ध्यान रखेंगे, which one is going to move in the Frankel defect? Only the cation is going to leave its site and going to occupy the intermolecular space. Interstitial में जाके वो बैठ जाता है. So it's a kind of interstitial defect, isn't it? In this case, the vacancy defect is created on its original position, and the interstitial defect is experienced at its new position. Did you get that? मतलब one side से अपने निकला, and in the same molecule, in the same unit cell, it is occupying its interstitial. So what will happen to the density? Is it going to change? Is it going to decrease or increase? No. Because the same unit cell is there and number of atoms are also same, only the position that the cation left its own site and goes to some interstitial site. So number of ions that remains constant per unit volume. So that's why the volume will not change. Okay. So in the Frankel defect, there is no change in the density. That's the point you have to learn. And it's a kind of vacancy as well as interstitial defect. दोनों ही आ जाते हैं इसमें. It is also known as dislocation defect. So why? Because only dislocate हो जाता है. Like in the class, you are supposed to sit on the first bench. Now you are not sitting on the first bench. You are sitting in, like you got the punishment and you are sitting between the two rows. So like this. So it's a what? Position change. Dislocate हो गया. The density of substance remains unchanged. Why it is like that? I have explained you right now, because number of particles is not going to change. Yes. It happens when there is a huge difference in the size of anions and the cation. Like अगर cation का size बहुत छोटा होगा, then only it will go in the interstitial, isn't it? और अगर almost बराबर होगा cation और anion का, तो that cannot occupy the interstitial. Yes, वो अपने site को छोड़ तो देगा, but interstitial को occupy नहीं कर पाएगा, and that's why Frankel defect. These are the 3 points, important points It is also known as dislocation defect. The density remains unchanged in this Frankel defect, and that huge difference should be there between the size of anions and cations. Cation बहुत छोटा होना चाहिए with respect to anion. Got it? Example ZNS AgCl. Sometimes it is asked as a example के type में पूछा गया कि in ZNS which defect occurs. So that you should know that there's size difference. Sulfur and zinc के size में there is a huge difference. Ag and Cl के बीच में huge difference. So that's why it will show that Frankel defect. And one example, let me write that AgBr also. Okay, why I'm writing, I will tell you. AgBr also. Now, see, this is the thing, Frankel defect, you they perfectly arranged, but now cation nikla apne side se and went to interstitial pe jaake baith gaya. So here it creates the vacancy, and here it goes to interstitial. Got it? So it is simultaneously it is creating an interstitial as well as vacancy defect, but electrical neutrality remains constant. Density remains constant. Got it? Okay. So now Schottky defect. Schottky defect is like same as a vacancy defect. This kind of vacancy defect is found in ionic solid. But in ionic solid, we need to balance the electrical neutrality of the compound. Because in that non-ionic, there is no tension, there is no stress to balance the atomic like electrical neutrality. But for the ionic solid, we are supposed to balance the what electrical neutrality. So इसमें क्या होगा? Schottky defect में equal number of cations and anions will leave its site. Got it? If one cation is coming out, one anion should also come out. If two cation is coming out, two anion will come out to maintain the electrical neutrality, and it will only create the vacancy, not the interstitial. And what about the density? Density will decrease because equal number of cation and anion are coming, and this is important point. Equal number of cation and anion will be missing from the compound. This is the very important point for the Schottky defect. If you will not write, it won't be considered as the correct. So density obviously it is going to decrease because number of atoms per unit volume is going to decrease, isn't it? In this, the size of cation and the anion are almost same. Then only they will come out together. Otherwise, cation, if smaller size, so cation will leave the position, leave the site, and will go to interstitial. But since cation and anion दोनों size बराबर है, that's why cation cannot be fitted into the interstitial site. So that's why it is bound to leave the site. So both the cation and anion will leave the site. Okay. Like you can see that the green one is cation and the red one is anion. So here from here that green is removed, and from here the red one is removed. You can check this key. Are the same type of lattice? Are the same type of atom? If it is like that, then it will be wrong. Got it? So you can see that this is the pattern: green, red, green, red. From here, the green one is missing. From here, the red one is missing. That means it is a negative ion is missing. And here, the positive ion is missing. So it is going to decrease the density because number of atoms will be decreased. But electrical neutrality will be maintained in both the case, Frankel defect and the Schottky defect. Got it? Frankel defect is a kind of vacancy as well as interstitial. But Schottky is only a kind of vacancy defect. Clear? This is the thing. Schottky defect, we can see that the pink one is missing, the blue one is missing over here, isn't it? In this case, आप देख सकते हो, the pink one is missing from its side, but in the same unit cell, it is there in the interstitial. Got it? So this is a kind of Frankel defect, but this is a kind of Schottky defect. Non-Stoichiometric defect. In this defect, the cation and anion ratio is disturbed either because of adding or removing of ion. या तो cation or anion, या तो we will increase the cation or we will decrease the cation and anion. Got it? Like there will be some changes. There will be some number of cation or anion will be changed. So obviously stoichiometric जो होगा coefficient होगा, that will be disturbed. But while in that stoichiometric defect, there was no disturbance. Stoichiometric will always be remain constant. If whatever the number of positive, the same number of negative anion will be there. But in this case, cation and anion size number can be different from its expected one. So that's why it comes under non-stoichiometric defect. Clear? Types of non-stoichiometric defect, it is metal deficiency defect. Like there are two type of things. Just okay, let me explain first and then I will tell you. That is the types of non-stoichiometric defect. This first one is metal deficiency defect, and in the second slide it is the metal access defect. Metal now what is this? Let me explain. Okay, metal deficiency defect. Suppose that in this case, how many cation are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 cations are there and 9 anions are there. Okay. Sorry, 10 cations and 10 anions. Suppose that 10 cation and 10 anion are there. Any problem in this? Okay. What will happen in this case? Metal deficiency defect. यानी कि cation should be less. Cation का number कम हो जाएगा. So that can be done in two ways. Either this anion will increase by one more. Either it becomes 11 and this remains constant. So that in that case, it will be called anion access defect. So much my bad what I'm saying? Like this is metal deficiency defect ना? So metal should be, cation should be less. So दो तरीके से हो सकता है. या तो anion का नंबर बढ़ जाए तो भी cation कम हो जाएगा, या cation का नंबर डिक्रीज हो जाए तो भी cation कम हो जाएगा. Did you get that? Two ways. Yes. 10 cation, 10 anion are there. What I have done, I have added one anion over here. In this case also, metal deficiency occurs. Or another case, I have removed one cation from this. In this case also, one cation will be less and metal deficiency defect will be. Got it? In this, the solid have less number of metals relative to the described stoichiometric coefficient. So much my baat, you can see that one cation is missing over here. So since it also occur in the ionic solid, so obviously electrical neutrality should be maintained. So what will happen? One cation is missing. If the cation is missing, so neighboring cation will start showing higher oxidation state. समझ में आई बात what I'm saying? Electrical neutrality maintain करने के लिए what will happen? If cation is missing from that, then the neighboring cation will start showing the higher oxidation state. Like अगर Fe+2 होता है यहाँ पे, तो Fe+2 गायब होता तो इसके लिए क्या होता है? ये Fe+3 हो जाता और ये भी Fe+3 हो जाता. Then only the एक Fe2 का जो what we say deficiency है वो overcome हो पाता. Got it? So the neighboring cation will start showing the higher oxidation state. That is called metal deficiency defect. So next is metal access defect. अब ये metal access defect भी दो तरह से हो सकता है. Again same चीज I am writing 10 cation and 10 anion. ठीक है? So that can be हम metal को access दो तरीके से कर सकते हैं. What one? Either I will increase one cation, तो 11 cation हो गए 10 anion, or I will decrease one anion, तो 10 cation हो गया और 9 anion हो गए. इन दोनों केस में क्या होगा? Metal will be access. Clear? So ये दो तरह के होते हैं. That I am going to explain this, and this is important part. वो ज़्यादा important नहीं था metal deficiency, but this one is more important. Okay, than that. So metal access effect. These are also again of two type. What is this? I am going to explain this. This is, let me mark as a main point. This one is the main point. Okay, and this is the sub point. So metal access defect due to anionic vacancy. That means anion will be less. One anion will be less. This occurs due to the absence of anions from its original lattice site in the crystal. Anion missing होगा. So what will happen? Cation will be more. ठीक है? Therefore, instead of anions, electrons occupy their position. अब ये चीज क्या है? Anion is going to miss. ठीक है? It is missing from its lattice site. So अगर anion को हम निकाल देते हैं तो there will be disturbance in the electrical neutrality. But I said that for the ionic compound, the electrical neutrality should be maintained throughout. So how to maintain? What will happen? In this case, it is generally occur due to the heating. Okay, what will happen? The anion, suppose that ZnO I am taking. Okay, this is Zn plus 2. Let me write. Like this is Zn plus 2 and this is O minus 2. Similarly, Zn plus 2, O minus 2. Similarly here, O minus 2, Zn plus 2. ऐसे होंगे. Okay. So what will happen? This anion will leave out. ये anion जो है, oxygen will go, but these two electron जो excess electron इसके पास था, that will be trapped by this center, trapped by the lattice. Got it what I am saying? So this anion will come out, leaving behind its electron in that site. Or you can say that the electrons of that anion will be trapped by the site. And that site is called, that trapped site is called Farben center site, F site. Okay. And due to which it shows the color, it imparts the color. I will explain afterwards. We chalte hain. So ये छोटा सा point था that I have explained over here. Therefore, instead of anion, electrons occupy their position. समझ में आगे बात ये clear हुआ point? Anion as an atom will go out and its electron, जो भी excess electron उसने ले रखा था, that will be trapped by the site. So in this way, negative charge is there in the site. So electrical neutrality will be there, isn't it? Because neutrality के लिए तो plus and minus charge should be equal, ना? इससे मतलब नहीं है कि cation कौन है और anion कौन है. Yes? चलिए. And the another way which I have explained that cation को एक increase कर दूंगी. So metal access defect due to presence of extra cation at interstitial site. इसमें क्या होगा? जो fixed है वो तो fixed रहेगा. साथ साथ interstitial पे एक और cation आके fit हो जाएगा. Got it? So these cation occupy the interstitial site in the crystal and the same number of electron goes to neighboring interstitial site. जो कि electrical neutrality should be maintained. अब अगर यहाँ पे इस unit cell में अगर suppose that कहीं आके अगर cation, if it is going to occupy the interstitial site, so obviously the electron, this will cation, how it forms? By losing the electron. So whatever the electron it will lose, that will be occupied by another interstitial site. So again the electrical neutrality is maintained. समझ में आगे बात what I am saying? Yes. Suppose that Na plus Cl minus Na plus Cl minus is there. So one more Na plus will come in the interstitial, and to maintain that electrical neutrality, one electron will also occupy the interstitial of that compound. Clear? समझ में आगे बात? You can see that metal access due to anionic vacancies. Anionic vacancies के लिए क्या हुआ? यहाँ से देखो, this anion has left, leaving behind its electron. ये electron cloud को यहाँ पे क्या कर दिया? छोड़ दिया इसने. Got it? This is the minus charge. Electron को यहाँ पे left. Okay. Now this one you just check. In this interstitial, ये metal एक और cation आके fit हो गया. तो दूसरे interstitial में what happened? The electron came, isn't it? To maintain the electrical neutrality. अब देखो जितने cation है उतने ही anion है. मतलब जितने plus है उतने minus है. Still it is like that. एक प्लस बढ़ा तो इसको मेंटेन करने के लिए एक नेगेटिव चार्ज भी आ गया. क्लियर? सो दिस इज द मेटल एक्सेस डिफेक्ट ड्यू टू इंटरस्टिशियल कैटायन. एक इंटरस्टिशियल कैटायन आ गया. एनी डाउट इन दिस? ओके. नाउ दिस इज द impurity defect that we will do in our next class. Okay, so here that's it for today's class, and in next class we will do that impurity effect, and I will tell you about the Farben center, F center, and how it imparts the color and the question based on that. So I hope whatever I have explained you got it. Make short notes, key point, write down. Okay, and revise the video properly, watch the video properly, and we will meet you in next class with the defect, another defect, impurity defect. By the time, thank you class, enjoy your study.